With the advent of antibiotics, the world changed. Antibiotics instantly turned many deadly, life-threatening bacterial diseases into simple, treatable illnesses. It seemed that these amazing new medicines had forever saved us from these harmful, diabolical bacteria. But over time it became clear that this is only the beginning of a long war with the microbes, a war we are now losing. Even millennia ago, our ancestors used all available means in their struggle with ailments caused by microorganisms. In Egypt, patients were given beer to fight these deadly diseases, and in China, soy drinks. Of course, such methods rarely saved one from death, and only in 1928 did humanity find a then radical new remedy against bacterial infections: penicillin. Officially, the author of this amazing discovery was the British bacteriologist Alexander Fleming. And so, from the 1940s to the 1960s, the golden age of antibiotics was upon us. From the middle of the 20th century, new drugs began to seemingly appear non-stop, one after another. But unfortunately for us, bacterial infections have gradually acquired resistance to each and all of these drugs. Because of this resistance, making effective medications has become much more difficult. And believe it or not, for the last 25 years now, no new antibiotic has been invented. If we do not soon reverse this situation, then, according to doctors, in the near future, we must expect a bacteriological apocalypse. Due to this developed resistance of bacterial infections to drugs, more people will soon die each year than are now dying from cancer and diabetes combined. So, you may ask, what exactly are these powerful weapons that microbes possess that medicines cannot cope with? They are natural and acquired bacterial resistance. Natural resistance is inherent genetically. Some pathogens, due to the whims of evolution, appear impervious to certain groups of antibiotics. This is determined by several factors: the structure of the protein membrane of the microbe, the number of receptors on its surface, and enzymes produced with the ability to disguise the microbe. The appearance of acquired resistance is associated with the process of natural selection. As a result of genetic mutation, some microorganisms develop resistance to whatever antibiotic is used against it. They transmit these new features to subsequent generations, and as a result, a whole strain of resistant bacteria is formed. And frighteningly, their number is growing by leaps and bounds. Remarkably, bacteria are quite simple and live for only 20 to 30 minutes. If nothing hinders them, their existence ends in cell division. In other words, every half an hour, there will be 2 cells in the place of the previous 1 cell, and by the end of the day, roughly 70 generations will have been generated. That is, from an evolutionary point of view, time for bacteria flows much faster than for the rest of us. This means that they rapidly develop through natural selection, and no matter how powerful an antibiotic is, even among, let's say, its 1 billion victims, at least one will be left standing thanks to a randomly acquired mutation. Often, antibiotic enthusiasts are blamed for the rapidly developing resistance of bacteria, as they use antibiotics at even the slightest hint of a sniffle. In fact, immeasurably greater harm is caused by the mass use of these drugs in animal husbandry. Imagine, more than half of the world's volume of antibiotics are used specifically on cattle and poultry. In a study published in the journal PNAS, it was estimated that in 2010, more than 63,000 tons of such medicines were added to the feed of animals in the world. This prevented a number of infectious diseases and reduced animal mortality, avoiding major economic losses. Microorganisms adapt differently to the actions of different antibiotics. For example, a bacterium that causes pneumonia in people with immunodeficiency has managed to develop a way to strengthen its cell wall. Other bacterium essentially pump the attacking antibiotics out of cells with the help of specially developed protein pumps before the medicine has time to act. We must also consider the fact that in the past, pathogens developed resistance to a single antibiotic. In cases like this, doctors used combinations of several drugs to kill the pathogens. But over time, the bacteria developed resistance to these combinations of antibacterial agents that differed in their chemical composition. This greatly exacerbated the situation. According to official estimates, due to the growing resistance of pathogens to antibiotics, at least 700,000 people are already dying annually. But it's impossible to accurately calculate the number of victims. And in fact, there are probably many, many more of them. The situation with tuberculosis is especially alarming. In 105 countries, there are pathogens with resistance to multiple antibiotics. According to the World Health Organization, in 2014, such strains were found in 480,000 people. More and more often, patients are picking up these infections resistant to antibacterial agents when they go to the hospital to treat other ailments. It's enormously difficult to rid the body of such dangerous pathogens. To undergo a course of therapy takes a very long time and is quite expensive. This is obviously not affordable for everyone or in all locations, and is the reason why the mortality rate from such pathologies is growing. To improve the situation, microbiologists, chemists, and pharmacologists are looking for new molecules with stronger bactericidal properties or are changing the structure of existing ones. However, in this case, the human imagination is far from boundless, and it's already supremely difficult to keep up with the various new mutations. Further, it will become only more difficult in the future, and at some point, the creation of new antibiotics will simply cease. Over the past 20 years, many large pharmaceutical companies, for example Pfizer, Eli Lilly and Company, and Bristol Myers Squibb, have reduced the number of new antibiotic drugs they are developing, or even completely shut down their projects for creating such drugs. The reason is not only that it's become more difficult to look for new antibiotics. An important role is played by the economic component. It's, for example, much more profitable to look for new medicines for oncology or the treatment of depression. If we stop doing research, then in the future we run the risk of encountering a disease that has no antidotes. In terms of the scale of consequences, such an event could be quite comparable to the Black Plague epidemics that raged through medieval Europe. More than a third of the inhabitants of that part of the world were killed by the Black Death, and that happened more than once. In the absence of effective antibiotics, an even more formidable pandemic could begin, one which could be capable of destroying perhaps 80% or more of the Earth's inhabitants. It's not possible to predict where such a blow would come from. Those species that were quite harmless yesterday may turn into disease-causing killers tomorrow. A clear example of this is HIV. Its predecessor, a virus causing immunodeficiency in monkeys, mutated, jumped the species barrier, and took root in the human body. So, can we win this arms race in which bacteria have such a clear advantage? In fact, there are alternatives to antibiotics. Some of them are at the beginning stages of study. Others are already undergoing clinical trials. Still others require no medical intervention at all and are based solely on common sense. One of the approaches to solving this problem is to attack pathogens of infections with their natural enemies. We're talking about bacteriophages, viruses that are parasites of bacteria. They infect bacteria and reproduce inside of them. They are also able to evolve at lightning speed and to bypass the enemy's resistance mechanisms. However, it's not yet clear how these phages behave when faced with the human immune system. And in general, there's no guarantee that, even having penetrated into the cell of a pathogen, the phage immediately destroys it. Another effective but still little-known weapon is antimicrobial peptides. Since the whole defense of bacteria is built on changes in their protein component, why wouldn't potential new antibiotics choose something different as its target? Among non-protein compounds, this something else is likely to be phospholipids, universal building blocks for any cell membrane. If the integrity of the membrane is broken, the bacterium will die. This is the weapon that most of the antimicrobial peptides use. No less successful a solution can, of course, be timely vaccination of humans and domestic animals, which allows us to develop our own immunity. As a result, the number of carriers of harmful bacteria will decrease, and the number of pathogens will inevitably decrease as well. Finally, common sense can help us win the war against harmful bacteria. Don't keep antibiotics in your home first aid kit just in case. And don't take them at the first sign of illness. Self-medication, together with ignorance of the correct dosages, creates perfect conditions for pathogens to develop resistance. It's better to allow the immune system to do its normal job and save the antibiotics only for extreme cases. In the meantime, the war between people and pathogens continues. Perhaps it will last forever. To survive, we must intensify our development of antimicrobial agents. This will allow us to get at least a few steps ahead of our small but extremely dangerous enemies, the deadly bacteria.